Can you see it?
Yes, Christoph, go ahead.
Welcome to my presentation about classification methods for motor vibration in predictive maintenance. First, a short overview of the content of this presentation. To begin, an introduction of the project in which these results were reached. After that, a description of the general procedure for the comparison of the methods. Next is a depiction of the test setup used to get the data with which the methods were tested. Following that is a list of the different sensors which are used to collect the data. Then I will describe the methods used to preprocess the data before classification. After that, there is a chapter describing how the different methods are evaluated and compared. Then the results are listed, and in the end, there is a conclusion and a short outlook. The project is a research cooperation between the Heilbronn University of Applied Science and the Saracon GmbH in Weikersheim. The goal of the cooperation is the development of a new type of thermal system with predictive maintenance functionalities. These thermal systems are used to cure one-component sealants after they have been applied to their devices. First, we created a set of labeled data for each sensor. After that, the machine learning algorithms were trained on 10% of the data. Then the trained algorithms were tested with all the available data. In the end, we created result matrices for each combination of sensor, conditioning method, and algorithm. In this slide, you see the test setup used to generate the data. It is a fan motor of IBM Papst on which crankcase 4 sensors are mounted. The 4 depicted sensors are all 3-axis accelerometers. The vibration of the motor is measured for 2 minutes with constant speed. The corresponding label for the classification is also recorded. The measuring of the vibration was done in an idle state of the motor and in 6 different rotation speeds. The sensors used to measure the vibration of the motor were as followed. 4 different 3-axis acceleration sensors. 1 3-axis acceleration sensor with 3-axis yaw rate sensor, a gyroscope. 1 3-axis magnetic field sensor and 4 multi-sensors which measure acceleration, yaw rate, and the magnetic field. On this slide, there is a visualization of one such dataset. It depicts the spatial acceleration in X and Z orientation of the MMA 8451 acceleration sensor. The 7 different rotational speeds are highlighted in different colors. In the idle state, the motor has almost no vibration, which can be seen at the small black dot in the middle. The largest vibration happens at 80% of the maximum speed, where the spread of the values is at its greatest. As all 7 point clouds are centered at the same point, a good classification based on the vibration is not possible. Because a classification based on the raw data is not feasible, we used some pre-processing methods to get a better classification result. First, simple differencing of successive values with an additional absolute value. Then the opposite, an integration of successive values by calculating the area between them. The third method can be used in addition to the first 2 or simply on the raw data itself. It is a moving average with the interval of capital G. On this slide, you see the difference between conditioned and unconditioned data. The left picture is an acceleration sample in X orientation. It has about 2,000 values for each speed category. Again, the highest acceleration values are at 80% of maximum speed. In the right picture is the same acceleration sample after differencing. You can see now that each speed category has its own value range, which makes the classification much easier. Here is the same process as on the slide before, but with 2 dimensions. On the left, again, the unconditioned data. It is just a big cloud of points all in the same space. Only the resonance at 80% of maximum speed is clearly visible. On the right side, after conditioning, you have 7 rather good delimited clouds for the different speed categories. Here are the machine learning algorithms we used for the classification of the motor. Decision trees, gradient boost, focused cluster algorithm, and artificial neural networks. In the course of testing, we found that the neural networks were too excessive for a classification like this. The computing time was multiple hours long, and the overall performance was on par with the other algorithms, which took only about a minute to compute. Therefore, we omitted the neural networks in the final results. Here we see the result of a classification with the focus cluster algorithm. On the left side with the raw data, and on the right side with different data. These confusion matrices show a distribution of the predicted results given by the algorithm. On the x-axis you have the classes predicted by the algorithm. On the y-axis are the real classes given by the data. The blacker a square is, the more its combination was given by the algorithm. In the left matrix you see the algorithm has only given the 3 classes to all the data, namely the classes 0, 4, or 5. This means the idle state and 80% and 90% of the maximum speed, respectively. As all classes were equally distributed in the dataset, this prediction had a performance of only 30%. The right matrix shows a black diagonal line. This means true classes and the classes assigned by the algorithms are almost always the same. This prediction had a performance of 98%. On this slide, you see a result matrix for the GY521 voltage sensor with the gradient boost algorithm. The 3 rows show the different conditioning methods, and the columns show the performance and the time needed for training and testing, with or without an additional moving average. As you can see, the highest performance happens with the unconditioned data at 98.51%. Here is the comparison of the 3 machine learning algorithms with the best performing conditioning method for the ADXL345 accelerometer. The columns show the 3 algorithms and the best conditioning method for each algorithm. The rows show the performance and the time needed for training and testing. The highest performance has the focus cluster algorithm with differenced and averaged data at 98.98%. The fastest training time has also the focus cluster algorithm with only 0.32 seconds. The fastest testing time has the gradient boost with differenced data and averaged data at only 1.44 seconds. Here is the same comparison for the MPU 60.50 gyroscope. With the gyroscope, the gradient boost method has the highest performance while using the unconditioned data at 95.24%. For the processing time, the decision tree is the fastest with only 0.09 seconds for training and 0.28 seconds for testing. Now the last matrix with the highest performing multisensor, the GY521. Here the highest performance is reached with the focus cluster algorithm and differenced and averaged data at 99.89%. The fastest processing time was again with the decision tree. If only acceleration data is used for a classification of a motor, the combination of the ADXL345 with difference and average data and the focus cluster algorithm is the best option. With an additional magnetic field, the GY521 and the same conditioning method and algorithm is the most suitable. Now that we can categorize the motor based on its vibration, we can use this information to build a model which predicts different states of the motor to get an approximation of its remaining operation time. Thank you for listening to my presentation about classification methods for motor vibration in predictive maintenance.